Hey everyone, our group has been working on the Smart Intersection Cameras project. So the main goal behind our project is to create a 3D model of a street intersection. So we're doing this by having 3D cameras placed on each corner, and this allows us to have more coverage of the intersection, and we're doing it in 3D because in 2D you're only able to see the front of objects. So in 3D you will know its position in the intersection as well. And we're also doing this so that we can collect detailed traffic and pedestrian information. And this information can then be sent to smart cars that would allow them to operate and drive better. And we're also doing this because it would allow you to see around certain corners and blockages of the intersection, and it would allow you to detect people and cars as they're moving through the intersection. So some of the project methods and equipment we're using are, we're stitching multiple point clouds together from each camera. We're also using the Cosmos scale intersection that's in the back of the room. And the intersection has 4 Intel RealSense depth cameras placed on each corner. So we're also using Aruco markers, which are these markers that are in the image here, and they're placed on a cube that's in the middle of the intersection, and we can use the OpenCV library in Python to detect the Aruco markers. And this will also give us their coordinates, and we can then create 3D point projection based on the coordinates that we've collected and use the CABSH algorithm to find the optimal rotation of the point clouds to create a good looking intersection. We're also using ROS and RViz. ROS is the robotic operating system, and it allows us to easily stream from the cameras because there are many pre-configurations for RealSense cameras in ROS. It also allows us to have many point cloud viewing options, but there are some drawbacks to using ROS, such as the inconsistent transformations we get when viewing point clouds, and it's also time and resource consuming to install on our nodes.
So we worked on making our own methods for transferring point clouds so we wouldn't have to deal with the inefficiencies of ROS. So first we tried some open source algorithms. There's the EtherSense that we got from GitHub, and that's shown in the top right, which you could see is very low resolution, and it was hard to decode the actual points. So we decided to make our own method using OpenCV, pickle files, and Python sockets. So this resulted in a much smaller file size than ROS, and it was very easy to decode the actual points. It's shown in the bottom right. You can see everything's in color, and we can have the depth camera view overlay. And so one of the issues we were having is the Aruco marker detection code would find different markers every frame of the camera. So sometimes it would detect a marker and sometimes it wouldn't. So we just made a cache and worked with the OpenCV native data types to store all the markers detected. So you can see on the top right, the markers are kind of flickering, and on the bottom right, the markers are consistent. And this led to an up to 20 marker increase. So this helped our accuracy of our transformations. And in addition, we added more Aruco markers. So we discovered that the cube was not enough. So we actually just had flat pieces of paper in the intersection for more markers. And this resulted in a near perfect sort of calibration where you could see one point cloud is the point cloud viewed from one camera and the other is from another camera. And you can see that the crosswalks are almost perfectly lined up and the ground is even, which is basically exactly what we wanted. But obviously this isn't practical for real life. We can't have a giant cube with markers on it. So we'll need more realistic reference points, which would likely be traffic cones or something like that. And finally, for the detection part, we really wanted to send multiple point clouds at the same time. So before we were only using one, but we weren't actually streaming the live data. So we started working with that where the client would send the files from its camera and the other server would download these files and view them. But we had an issue where we couldn't load the local files and the received files at the same time. So these are the two images. The one on the top is the local files, which runs a little faster because it doesn't have to stream them. And the bottom is the files from the other camera. And so after we finished this calibration, we wanted to work on object recognition. So we used PyTorch and YOLO V8, which is a deep learning algorithm to start detecting people, cars, etc. And we were actually surprised with its effectiveness because we were using a model intersection with little human figures. And finally, we wanted to improve the car detection so it would work with the cars made by the other groups here, which obviously don't look like normal cars. So we took our own pictures and we're able to achieve up to 97.8% accuracy with determining if it's a car or not. And then we wanted to segment these images so we would get the points of where they're located, so we can sort of separate them and track them as individual objects within the intersection. And here you can see there's a detected person and the outline of all the points of where it thinks the person is. For future improvements, we would like to fix the point cloud video viewer so it can see all 4 cameras at the same time live. And we want to be able to translate the segmentations into 3D and create a sort of bounding box, as you can see around the 3D car. And that's it. Thank you.